Hello, I'm Sagacious, and Diablo 2 is one of my favorite games. I do a lot of pure mathematical proofing, formal logic, and a little bit of theoretical physics, and I want to dedicate this channel to taking a deep dive, an exploration at many of the mechanics in Diablo 2, as they'll be preserved in Diablo 2 Resurrected, so I'm very excited for this. In this video, I'm going to tackle the question of how Crushing Blow affects the damage dealt, and we're going to focus on the damage per hit in this video. So let's just dive right in. Throughout this video, for visual stimulus, I've just added some of these interesting three-dimensionally rendered models. People can compare and contrast them with the Resurrected remaster if it pleased them. So Crushing Blow, generally speaking, if and when it's applicable to a particular attack, first relies on a successful hit check. So the character moves in, there's a hit check. Once there's been a successful hit check that's passed, there is then a chance of Crushing Blow that is checked, and if that is successful, then a percentage of the monster's remaining life, as illustrated in the little picture here, is reduced. Then the character inflicts damage, and both of these, of course, are proportional to the target's resistance. That completes the one iteration of the simplified process that we're going to be focusing on. We're really going to start looking at just the first iteration, if you will. So the things we want to keep note of, well, the first is the initial amount of life that the target has before the first hit. We're looking just at the first hit, and we want to look at the chance that the Crushing Blow is triggered on that first hit. So we're assuming, for the sake of simplicity, that a hit has successfully landed. And that's fine. We could always factor that into our calculations later. I'll discuss that. We're looking at the percent reduction to the initial life before the first hit that occurs on the first hit. And we're looking at the amount of damage once that reduction has occurred that the first hit inflicts, if any. That could be physical, and again, we could account for the enemy's resistances, and we could even factor those resistances into the reduced life before the hit. So these are the things we're looking at. We're looking at L0, C1, P1, and D1. What we want is then to, from these, calculate L1, which is the amount that's going to remain after the first hit. That is, after this process has occurred, how much life is the target going to have left? Because we're going to be able to, by doing this, build a picture of how much life changes across time. Okay, so how would we do this? Well, we know it's going to involve the initial life before the first hit. Right, and we're going to reduce that when there's a check by some amount, which is illustrated in the red question mark. And when it doesn't occur, there's going to be no reduction whatsoever. And because C is the probability, this is basically like adding up the sample space of possibilities. So all the instances in which there is a reduction and all those in which there's no reduction, right? Well, since that's just 0 times the probability it doesn't occur, 1 minus C1, that's just adding 0. So that's fine. So we're really just looking at subtracting the subset of the cases in which there is some kind of reduction, and that gives us the expected reduction that will occur. Well, that's just going to be the percentage of the initial life. That's P1 times, right? You're just scaling the initial life. So L0 times P1. That product is going to multiply the probability. So there we have that. Now, what happens after that? We just have to subtract the damage we do on that first hit. Right, so that's going to give us, after the first cycle, the first iteration, the total remaining life after the first hit, excluding all other damage sources. We can factor out the L0 and just simplify the expression. So there we go. All right, so we have this iterative process for the first hit. And if you wanted to, assuming no other constraints, you could prove by mathematical induction that this, assuming no other constraints, would be true for any nth iteration in the sequence. So in other words, you could just generalize the highlighted 1 and n, 0 and n minus 1. That is, the n minus 1th hit would be the 0th hit if you want. And the nth would be the first. Then you can just generalize this to the following recursion relation, which is just a relationship that relates the amount after to the amount before, right? That's a fancy way of saying that. However, there are some complications. This isn't quite accurate, and there are a couple of reasons why. Although the Ariat Summit says that you die when you reach 0 hit points, that doesn't appear actually to be correct. So the Amazon Basin Wiki, which is a great source, it explains that units of life, that is points of life, are not the smallest unit. They're actually, the smallest allegedly is 1/256th of a point of life. And these are usually rounded down to the nearest whole point. And furthermore, numerous sources, the Amazon Basin being one of them, point to a character or monster dying if and when the life falls below 1 whole point, not 0. All right, and that's also consistent with this calculator in the Lurker Lounge I found, where there's a termination function for calculating the remaining life, where once it's below 1, it's just set to 0. So I haven't looked at the source code, but I conjecture from these pieces of data that, generally speaking, the recursion relation is more likely to involve a function as follows, where for any nth step where you have this equation being greater than or equal to 1 unit of life, it just sets L sub n equal to that, and when it's less than 1, then it just sets it equal to 0, right? You would technically have something like that, kind of a piecewise function, if you will. We're going to make some simplifications to this. We're going to approximate this recursion relation for a repository of reasons. Number one is that we want to keep this accessible to people. I don't want people to have to know, differential equations, linear algebra, etc. So I want to keep this accessible and useful to people so that they, most people who don't need to know advanced mathematics, can use this. So we're going to make many approximations with this. So I'm going to use this squiggly equal sign that you see here for L sub n, the life remaining on the nth hit, to approximate this recursion relation. And we're doing this, number one, the first simplification we'll make is we're not going to consider the basis case where we have that this left-hand side of the equation results in a value less than 1. We're just instead going to treat all the data points not as if they are discrete, but as if they were just real numbers, continuous values, and that this equation has no upper or lower bound of applicability or anything like that. It's just an equation, and we can start with even a positive value of life. And as far as our analysis is concerned, for the sake of simplicity, we can go into negative life, meaning we can just start with some positive value, keep iterating this process, and even go into the negative if we need to. And furthermore, choose L sub n equal to 0 if we want. So we're not treating the data set as though it's discrete, and we're not distinguishing the recursion relation for the basis case. And the reasons we're doing this should become more clear later on. Just to highlight some things in this equation in case it's unclear, again, L sub n minus 1, that's the life remaining for the target x before the nth hit. So this line, L sub n, it really pertains to what's going to happen for the nth hit. We're starting with the initial life, right, on that hit. C sub n, again, is the chance that crushing blow is triggered on that nth hit. And we distinguish this because maybe it even changes per hit, right? That's a factor to consider. P sub n is the percent reduction to L sub n minus 1. That is how much we're reducing that initial life. And again, we make the distinction of the sub n because maybe it varies with n. Maybe it changes. And D sub n is just the amount of damage inflicted on that nth hit once this occurs, right? So that's the idea. And obviously that implies that L sub n is the life that should remain for the target x after the nth hit, based on this simplification. So this is an approximation of the recursion relation for any nth hit. There we have it. So what? What's the big deal? That will become clear later on. Let's just continue with the abstraction for now. But again, we'll keep this as accessible as we can. So some reasons I just want to illustrate that this is an approximation is, as we previously discussed, we assume the same recursion relation for all n hits. There's no basis case we're considering, right? We didn't account for rounding in the game. So for example, many instances in a repository of calculations in the game, there's rounding. So for example, if you have some percentage of enhanced damage on an item from the base damage that item does, so particularly the item is a weapon in this case, the percentage may be to a fraction, but the game will often round that up or down. And so the rounding obviously will affect your results in the calculations. So we're not accounting for rounding. We're not accounting for rollovers, where perhaps there's a maximum number of digits that the game might process at any one time. And if and when you have an amount over that, it just rolls back down to the initial values, and the amount that it rolls over is proportional to that. We're not accounting for that, etc. We're treating the data set again not as if it were truly discrete. That would fundamentally change the system of equations we're using, but also complicate considerably the calculations. And in the interest of accessibility, brevity, etc., we're not going to get into that in this video, at least. We did not account for life regeneration, damage due to poison, etc. Those are also potentially confounding factors. Sometimes irrelevant, sometimes relevant. It would depend. Solution. So this is more of a conceptual point that solutions to differential equations, which is really what we're going to be talking about if we're getting advanced, they're often linear approximations of the solution curves within a neighborhood of the point in question, which is a fancy way of saying that error is often systemic to our attempts to find explicit solutions. So there's going to be error in there almost inevitably due to the form of these equations not being conducive to solving explicitly for the solution. So that error is almost systemically unavoidable given our methods of. I think that will become more obvious to those familiar differential equations as the video proceeds. So let's go back to the initial equation, which is again an approximation of the recursion relation for the nth hit. So we want to start making some simplifications, just so that kind of extends the power of analysis. And the first thing you'll notice is I move back and forth between these slides. We're going to change C sub n to C, right? That just the chance of crushing blow. We're first going to just say, well, let's just say that most often people are not changing for sufficiently small intervals of time for sustained attack. They're not changing the probability that they will have a crushing blow occur. They're not like swapping between weapons. But notice here that this is an important caveat. We are then kind of presupposing that we're not alternating weapons, right? For example, a barbarian could hit with, right hand, left hand, and the probability of crushing blow would then alternate. So that should give someone an intuition that there is a different set of equations we would use for making that calculation. Which, if you're interested, please let me know, comment below, and I'd be happy to make a video on the probability for crushing blow, considering double spring, frenzy, double throw, etc. Right? So, but for the most part, for many characters, we're just considering a consistent probability for a sustained attack over some period of time t of crushing blow. And similarly, we're thinking of the percent reduction to life as also rather consistent, right? It's not changing, which again isn't necessarily true. Say you have a weapon on that has a chance to cast amplified damage and it triggers during an attack. Well, obviously, that's going to affect the percentage reduction to life because that depends on the enemy's physical resistance. It could also be that while you're attacking, someone joins the game, and the percentage of reduction to life will change accordingly then, because it's a function of how many players are in the game. But again, for the most part, we're thinking of sufficiently small intervals of time of like 1 to 2 seconds, maybe 20 seconds for like long fights. I don't know when, but so we're thinking of the percent reduction to life is relatively constant. We're also going to let the damage, so this is a significant shift, be constant. But now that constant damage done will not be just the amount on that hit, but will be the mean damage inflicted per hit. And we're assuming that mean damage per hit is constant. So again, that has implications of the enemy's resistances. Does their resistance to fire or physical, does that change with time? And again, this damage could be damage after the resistances of the enemy are taken into account. We could even weight this damage according to our probability to hit if we wanted to. So that's where probability to hit could come in, where if there's a 95% chance to hit, we could scale the damage according to that probability to hit. And, in the same sense, we could scale the chance of crushing blow as well. That is, we could just change the probability of crushing blow according to our chance to hit. That is the chance of crushing blow given that we hit. So included in this equation, it has the basic variables in place already for us to account for those nuances. And again, in making this change to letting damage be a mean damage inflicted per hit, we're now talking about the life, both the initial and the remaining, being a mean. There are at least two ways in which the mean life remaining could be a mean. For example, it could be the result of prior mean damage applied, or it could, if you wanted to be even more general in your analysis, be the mean life initially of the monster, if it varies, independent of any damage taken, right? Or I should say before any damage taken. And, whereas in the final damage, it's just the mean life remaining because we're letting damage vary now, right? So that's the mean life remaining for the target. And again, technically it's after any nth hit because this equation is defined that way. So there we have it. It's pretty straightforward. Now, let's go back to making a calculation. Again, the squiggly just lets us know this is approximation. There are many variables that we haven't accounted for that could introduce error here and there. So this is an approximation, but let's try to express L2 using this equation, right? Well, we know it's going to be, if we follow the previous recursion relation, L1 times 1 minus PC minus D. And the shift in doing this, you'll notice, is that it allows us to treat PC and D now as just constants, right? Which is nice because then we only have to really worry about L sub whatever moving, So what we want to do is eliminate those subscripts. We want to remove the need for us to care about those so that we can express for any nth hit the life remaining on that hit in terms of the initial life of the target before any damage was done. That would be nice. So to do that, let's actually consider the L sub 1 and plug in, using the same recursion relation, L sub 1 in terms of L naught, the target's initial life in this case, right? So then let's distribute. It's just multiplying. So what you'll notice is this last D on the end of the right-hand side of the third row is just times 1, but 1 minus PC to the 0th, that's just 1 on the right-hand side of the bottom row, right? And D times 1 minus PC, that's just D times 1 minus PC to the first. So this 1 minus PC term always, and you can prove this by mathematical induction, if you wanted, under these assumptions that, it'll always start, in this case, it will always, but in the case of 2, it starts, L naught times 1 minus PC to the power of, well, what's the number of the hit? In this case, it's 2, right? And then minus D times, 1 minus PC to the first, and then minus D times 1 minus PC to the 0th. We can focus our attention really on by factoring out the D, because it's a common factor to those last terms, and just observe that that's a sum, and you can put it in summation notation as indicated in red, right? And we're just what we're saying is that K indexes 1 minus PC. And all that symbol says is to add 1 minus PC to the 0, because K varies from integers, 0, and then on up to 1, and then it stops. So it's the same. It's just saying 1 minus PC to the 0 plus 1 minus PC to the 1. All right, and so L2 is just the initial life times 1 minus PC to that second power. And you'll notice the correspondence between L2 and that second power again. Minus damage times the summation of K from 0 on up to, well, look at that 1. That's just 1 less than the number of hits we considered. And that's not a coincidence. You can prove by mathematical induction that that will always be true under these constraints. So L sub n, again, is just really more generally by mathematical induction, L naught times 1 minus PC to the n minus D, and then you're just multiplying D, your mean damage per hit, with or without resistances and probability hit, etc., times the summation as K varies from 1 to the n minus 1. That's all that's going on. So we have this equation, and now we've got this n. It's looking like we can do something with that in a moment, but we also have an opportunity to change the L naught now, right? Because then I can change L naught to just L. There's no need to consider a subscript because now I don't have to worry about that. I can just express the life remaining, again, the mean life remaining for some target on the nth hit in terms of the target's mean initial life. And it doesn't have to be a mean, right? But if you wanted to generalize to, the variance of the target's initial life, you could. You could also imagine L to be whatever life is remaining. It doesn't have to necessarily be the target's initial life, right? It could just be whatever you started to do the attacking with. But now we can just write this in terms of 4 constants, which is nice, so you can just look this up, see the monster's initial life, put in a chance of crushing blow, a % reduction to the life, and the mean damage inflicted per hit. And you can use that through damage calculators online and just factoring in the resistances of the monster. And that damage doesn't necessarily have to be physical. You could add the physical with, the resistance considered. You could add the fire, etc. Right? So, and again, you can scale the % reduction to life according to physical resistance. So we have this nice equation, but again, it's still an approximation, right? So I want to focus your attention to this summation because it's we would like to put this in a form where we can just plug and chug for most people. We don't want to do too much analysis to use it or think about it. So we're going to focus on making this simplification. So we're going to assume that the product of P times C is greater than 0 and less than 1. And this isn't really too problematic because think about what this equation is talking about. It's talking about cases where we have a probability to do a crushing blow. So C isn't 0, right? And that there's some percentage removed. So P's not 0. So, both of those things, the probability being greater than 0, that's fine. That makes perfect sense, right? Because then we're saying there's some amount that will be reduced that's non-zero. And there's some chance that's non-zero that it occurs. If there was no chance, we don't have to use this equation. And we're saying, well, we don't need that percentage ever to be 1 because there aren't really any instances in which crushing blow ever reduces something's remaining life by 100%. So P will always be less than 1. And so we can account for C being equal to 1. That's fine. That is when we have a certain, 100% chance of crushing blow. Well, even so, if P is always less than 1, 1 times P is still going to be less than 1. So letting these things, that is their product, be between 0 and 1, that is strictly, letting PC be greater than 0 and less than 1, that's fine. That makes perfect sense under the constraints and with but anyway, if we do that, one of the reasons we'll do this, which again will become clear later, is again, by assumption, if it's greater than 0 and less than 1, then multiplying both sides by a -1, well, that just, flips the sign. And then adding 1 to all sides of the inequality, well, that just means what we can show is 1 minus PC is just between 0 and 1, right? So that will become more obvious later, but it also again, PC is strictly positive. So here's why one reason we care about this is this partial sum in the previous equation that, it's kind of, we'd like to just put it in terms of something we can compute. This is actually equal to 1 minus PC to the nth minus 1. That is -1 times that. You'll see a minus sign there, divided by PC. So seeing that PC is strictly greater than 0 lets us know that that denominator is non-zero. And so because of that, which makes, again, it makes perfect sense why we would make that constraint, and it just lets us know that this equation makes sense. So we can substitute this equation for that partial sum. And so let's do that, right? So we have the previous equation for the life remaining up to the nth hit, and we're just going to substitute the equivalent under these constraints, again, where 0 is less than PC, less than 1. And notice we have a minus sign and we minused the damage. So distributing that as a double negative, we'll just be adding that, right? So we have a simplified equation, or, a clearer equation that we can plug into. So this is what we have, right? And now again, we have this n that we can now do something with. That's the total number of hits, right? And we can now express, choosing a number of hits, the mean life that will remain for a target given those number of hits after they occur, right? All we need to know is the target's initial mean life, the chance of crushing blow, percentage of reduction in life, right? So, and the mean damage inflicted per hit. And again, the comma next to the equation is just letting us know the constraints under which we define this equation. So here's our approximation of the mean life remaining for a target X after the nth hit, right? And again, those squiggly lines let you know, and you see the constraints. So that's great, And notice here's what's nice is we have only 5 variables that we really need to consider. That's not too bad, So let's do an example. When I initially posted this, I'm sagacious, by the way. I did this in the Amazon Bastion a couple of years ago. And I gave an example here, and the source, the links for all sources will be provided, where we suppose a character inflicts 1 to 3 damage per hit. And right now we're assuming it does hit for every attack, because again, we've already discussed how we could factor in the probability to hit. And the target possesses 100 hit points. That would be 100 life, as we define it, initial life technically, and we could treat that as the mean if we want to. And that for each hit, the character has a 50% chance to reduce the target's remaining life by 25%. So the percentage reduction is 25%, the probability of a crushing blow is 50%, the initial life is 100, and the mean damage, well, you take 1 plus 3, right? Well, all right, before we do the calculation, let's proceed with, if we didn't have this formula, how would we do this, right? Well, for the first hit, because we're only looking at the first hit, for the first hit, either it does or it does not reduce their life, right? We either get the crushing blow or we don't. Well, there's a 50% chance, right? So 50% of the cases, it's reduced by 25%, and 50%, it will not be reduced by 25%. And it has 100 hit points, right? So, and in each of those cases, there are 3 subcases, right? Where 33% of the time, because the damage range is inclusive 1 to 3. So it's either going to do 1, 2, or 3 damage. Well, that means 33% of the time. So we're assuming here sufficiently pseudo-random spread of how the game handles number generation. Also, it's important to consider. But so, we're either going to have 1, 2, or 3 damage in 33% of the time for each. So factoring that in, right? So we have 6 possible cases. We let Y denote that it did trigger, and no denote that it didn't trigger, and then 1, 2, 3 is just the other coordinate for the 2 tuple. So Y1 means yes it did and we did 1 damage, and N2 would mean no it didn't trigger and we did 2 damage, right? So there's 6 cases, and let's see what the life remaining up to the first hit would be. Well, we see each of them. It's 74, 73, 72, right? And that's just taking 100. So in the first line, Y1 means yes it did. So we reduce 25%, and 100 times 21 minus 25%. So that means that's the same as multiplying 100 by 75%. That's going to give us 75, and we did 1 damage, so 74, right? So we have all those. All right, so what would be the average amount of remaining life? We'll just take the mean, right? That's mean by the average. So we just add those and divide by the sample space of possibilities. That's 85.5. Well, using this this formula, we don't have to do that, right? We know the mean damage. It varies 1, 2, and 3. We're assuming it's sufficiently pseudo-random. We can treat it as random. They're equally weighted. Divide by 3. So the mean damage is 2, right? So D equals 2. And we already know the other values, so we use that equation, right? And by using that equation, we get the exact same value. So that's how this equation is useful, right? It tells, because obviously it's going to get less and less practical for us to have to make that check as the number of hits increases, right? And it's going to take more time for a computer to make those calculations as well. So this equation is just a shortcut, or a shorthand, if you will. It allows us to do that. And it's still an approximation because, again, it doesn't account for many of the subtle nuances that would introduce error into our calculations. But it's reasonably accurate. But now, let's make this actually more useful. So we want to solve for an approximation of the mean number of hits to kill the target with crushing blow. And this will become more obvious why we need to do this, or want to do this later. But we do this by setting the initial value, that is L sub n. I'm sorry, not the initial value. The life remaining after some n number of hits. Let's set that to 0. And the thinking there is, again, even though the target probably dies for less than 1 unit of life, we're going to make the simplification that it's just 0, which won't matter too much, as should soon be shown. And again, we could calculate for n less than 1. It would complicate the equations, and I want to keep this accessible for people. So if we let L sub n equals 0, what we're saying is choose the mean remaining life to be 0. What will be the number of hits to do that under these constraints, right? And that's where we would solve for n, which is the number of hits. So we're going to set L sub n for the previous equation equal to 0 and solve for n. Again, so we also keep in mind the constraints. So if we have 0 less than PC less than 1, so I have equal signs here because I'm not saying, I don't want that to be conflated with saying now things are not approximations. I'm saying that we're setting the right-hand side equal to 0 and solving for n. So that, I don't want that to be confused here. But by doing that, we can subtract L times 1 minus PC to the n from both sides of the equation. And then what we can do is just multiply -1 by both sides. And after that, of course, all we have to do is take factoring that -1 in. So we have 1 minus that, 1 minus PC to the n, over PC. And then we just multiply both sides of the equation by PC. So cancellation of PC on the right-hand side of the equation, right? And we just have LPC because we don't need those parentheses, coordinates to closure of real numbers or integers, whichever you prefer. So, we have this equation. Now we're going to want to isolate n eventually. But before we proceed, we're going to be dividing by that d, that damage. And, usually when we're thinking about damaging a monster in this context, we're assuming we do some damage, right? Because if all we could do is constantly reduce their life, but in this model, it asymptotically approaches 0 but never reaches 0, we're never going to kill that monster. So we need some damage that's eventually going to kill the monster. So we're going to let D be non-zero, not only because it makes sense in this context that, we're doing damage, not just applying crushing blow over and over and over, but moreover, it'll allow us to continue with the next step, which is to make this division, right? And you noticed earlier, so now we're assuming PC is greater than 0 and less than 1, which again is perfectly fine, and that D is non-zero. That is, it's greater than 1 more specifically. We just chose D to be greater than 0 rather than less than 0 because usually the sign we're thinking of is positive numbers, probably just a reflection of how the game handles numbers. I don't know. I haven't looked honestly at the code. But in any case, this just allows the denominator on the left-hand side to be non-zero. On the right-hand side, well, again, if PC is between 0 and 1, we just showed that 1 minus PC is going to be a non-negative value. So it's greater than 0 and less than 1. And to the end, well, that's just going to put that to some positive, the output will be non-negative. So we don't have to worry about that denominator being 0 on the right-hand side. So that's fine. So, we can separate the difference in the numerator for that fraction on the right-hand side. So we have this, and then we just add the 1 to the other side of the equation. Now, another caveat is, well, we're about to solve for n, we're about to take a natural log, and we don't want to have a natural log of a negative number. You can define natural logs for complex numbers, but it's a very different function, and we want to keep this accessible. So again, since we're talking about a monster that's alive, let's just say, it could be arbitrary, but let's just say L is greater than or equal to 1, right? So life in this, and that way we can't have a negative life put there, right? So now we're saying that life is greater than or equal to 1, damage is non-zero, and PC is greater than 0, less than 1, then we can take this natural log, and on both sides of the equation it makes sense, right? Because 1 over something to the n power, which is between 0 and 1, that's either going to get really big or really small, but it's still going to be strictly non-negative. And the other side is also going to be non-negative because we have a product that's non-negative times something greater than or equal to 1, that's just non-negative, and then we're dividing that by something that's non-negative. If you add that to 1, it's a natural log of a non-negative, so we're fine. That's well defined. And again, these are all finite values, so we're taking a natural log of a finite value for each of these, so that's fine. And so by the property of natural logarithms, we then have the next step, that -1 times the natural log of 1 minus PC. We make that division on the next step, and we just have a negative n. We can multiply both sides of the equation by a -1, and we have our n, right? So we have an approximation now. The mean hits needed to kill a target with crushing blow is given by the opposite of this quotient, right? And we just note the constraints for how we define this equation. 1 minus PC, 0 is less than PC, less than 1, D is greater than 0, and we're just saying L is greater than or equal to 1, right? And notice what's nice here is we can now find the number of hits needed to kill something with only 4 variables, and they're all constants, right? The target's mean initial life, or you could just conceptualize that as life remaining, the crushing blow, percent reduction of life, and the mean damage inflicted per hit, right? So that's pretty nice. And here's an example. So again, I gave this example in the initial forum post in which I spoke of this. Suppose a character does 1 to 3 damage a hit, right? To a target with 100 hit points. Again, pretty much the previous example we used just for consistency, right? And it's got, again, a 50% chance to reduce the target's remaining life by 25%, right? So we plug in these variables, these constants rather. We plug in the values for these variables, which are constant. And we have that n is approximately 14.84, right? So I've done a lot of digging for calculators that calculate precisely this. And when I say precisely, I'm not saying these calculators don't have error. These calculators have error as well, some more, some less than these equations. And they have error for similar or different reasons than these equations. So that needs to be understood here. But one such calculator, which is still pretty reliable, has the mean number of hits to kill a monster at approximately 14.79. And the source is below it, of course. So, for relative to that calculator, if that calculator were more accurate, we're only about 0.27% error, or if you prefer variance, and the expected number of hits between these, in these for this example. So that's pretty nice. It's pretty consistent. But you also notice that that's because, the percentage of the target's initial life that their damage is per hit is much lower, right? They have a small amount of damage compared to the amount of hit points or the initial life of the target. So that's part of what's going on here, because you'll see that if we change this to say only 4 hit points, now our damage is very considerably, our mean damage is 2 in this case, right? So that's about 50% of the initial life, so it's significant, right? And you'll see the number of hits, of course, is 1.67 these equations, and that calculator would say 2. And so this calculator that I'm referring to, it actually factors in when a monster is below 1 health. It actually will terminate the calculation there, but again, it has its own inaccuracies. But even so, there's only a 19.76% error or difference, if you prefer, variance, shall we say, in the expected number of hits between this formula and that calculator. So that's pretty nice. Even when we take it to a situation where we're basically killing something in 2 hits, the number of hits that this simple equation produces as an expected result is still within about 20% error. That's not bad. So to solve for an approximation of the mean damage per hit, right, for the target with crushing blow. So now we can use the mean number of hits to kill the target from the previous equation and just take the target's mean life and divide that by those number of hits. And that gives us a good idea, or shall we say an analog of a mean damage per hit to the target that we would be able to do to kill the target in the same number of hits, right? And so that would be L divided by N, where N is the N in the previous equation, right? So plugging that in, and since you're dividing by the opposite of that fraction, you have a -1 times, so you just invert and multiply the fraction. So there you go, right? So we now have the following equation, right? So an approximation of the mean damage per hit to the target with crushing blow. All right, so that's, I've bolded this damage, this mean approximated damage as a bold D to let people know this is not the same as the mean damage inflicted that you would calculate, from a D2 damage calculator that you do per hit independent, without considering crushing blow, right, is given here. And we've stated the constraints for this equation. It's pretty nice because, again, all we need are 4 values, right? We don't even need to know N in this case. We only need 4 inputs. And so we'll do an example here, right? So one example I did in the previous in the affirmation post in which I initially discussed this was, if you have an average of 1 damage per hit to the target possessing, say, 100 life, and you've got a 60% chance to reduce by 25%. We're just using 25% a lot because that's typical of most normal monsters for melee weapons. Again, you could change that percentage. But if you do that and plug that into this equation, right, you're going to get approximately 5.86 damage per hit as the analogous mean damage you would deal, meaning if you took that life, divided it by that, you'd get a comparable number of hits, right? And that's about a 486.16% increase in the average damage per hit, right? So that's a huge amount of increased damage percentage-wise. And if you're wondering how close this is to, say, the previous calculator we mentioned, where you're factoring in, say, the instances in which it drops below that 1 life, and that's going to change whether or not it's still living. Well, you'll note that in this case, the equivalent damage, including the average damage, right, expected there is 6.21. That means you've only got approximately a 5.97% error, or again, we don't know if that calculator is as accurate, variance in the mean damage per hit that we would expect. So that's pretty nice. It's not too bad. So we can also use the previous example in a pretty interesting way. Let's say that we plug in all the previous values, but rather than putting a 60% chance of crushing blow, let's just say we let that C, that chance of crushing blow, be a constant. I'm sorry, a variable. So we want to see how this damage would change in this situation, just with, increasing or decreasing chances for crushing blow, right? Is it a linear relationship? Does it drop off quickly? And, the graph to the bottom right kind of shows you the y-axis is the mean damage with the crushing blow. That is the approximation of it. And the x-axis is the probability of crushing blow, holding the other variables constant, of course, in this particular example. It's just to illustrate that now with these equations, you can make a lot of qualitative assessments and really do some interesting things. So in this example, you see that it's almost linear. It's not quite linear, but you clearly get in the very beginning a huge amount just because it doesn't start at, it doesn't go right through the origin. But for the most part, it's a pretty linear increase in damage in this particular instance, but this is just to illustrate that there are a repository of applications that are very interesting that you can have with these equations. You can start to do a lot of interesting things. So for example, another thing you could do is you could look at, holding all the other variables constant, just let the damage vary. So plug in all those other variables, take just the damage, and you saw, we previously calculated the percentage increase in damage, and the y-axis here is an amount that when multiplied by 100 will give you the percentage of increased damage, and the x-axis here, that is the horizontal axis, is just the variance in the damage. So you can see near 1 where we had 1 damage, it's not clear from the scale, but that's going right through 4.86. and times 100, that's a 486% increase, right? So you can see right there that it's spot on to what we would predict. And it can, but what you see is with increasing damage, you get an asymptotic decrease, right? It's asymptotically going to 0, or in the amount of percentage-wise additional damage conferred, right? And the smaller your damage gets, you get exponential increases, and you can see that where it turns. So you can do all kinds of interesting analysis with these equations. And in future videos, I would love to dive into these and be much more thorough, but still accessible. So, but I want to keep these videos short, concise, and to the point. So now that I've kind of given some examples and just motivated some interesting applications, because that's what I love about these questions, or rather these equations, is they can be used to answer heretofore open questions, or at least better answer them. For example, you can use these to better answer, should I use that death with the probability of crushing blow that it gives me, or the increased crushing blow that it gives me, and does it actually win out? You can do a better job of that, but you can also use these equations to see, how close and how accurate are certain, calculators out there, rather than just taking it on faith that the people who made them did them correctly. But you can also see that, and I hope one lesson from this is that it's not really that there's one way to compute this, because sometimes the systems of equations will blow up to become very inaccessible and very complicated very quickly as you factor in, many details. And so sometimes it's a question of picking and choosing, like, what's a nice way to approximate this? Is perhaps a good way to look at this for problems like crushing blow and how it factors into damage. But now that I've discussed that, I want to talk about a few calculators. So this first calculator you can find if you do a search. It's www.dos486.com/crushing/. So this is an outdated calculator because as highlighted, you can see that the second term is the life removed by the halving done. That no longer is mechanically how crushing blow works. So that calculator is no longer accurate with the current version of Diablo 2, Lord of Destruction, nor is it accurate with Diablo 2 Resurrected. All right, so equations rounded, okay? So this is an important note. And again, the source is below. You can go to the actual initial form in which I discussed this many years ago. Back then, there was a calculator. It was a German calculator. Unfortunately, the link is broken, so it's no longer accessible. When you round, and you can see how you round, you use a floor and ceiling function. But when you apply, you preserve functions, the equations in this video as discussed, exactly as they are. That is the form of them. And you just apply a ceiling and floor function, and they exactly replicate the results of the German calculator. As this citation demonstrates, it's worth noting that these equations can be used to calculate the exact outcomes of this calculator. Unfortunately, again, that calculator is no longer available. The link is broken. If you happen to find it, please drop me a link in the comments below. I'd really appreciate that. So thirdly, this calculator is reasonably accurate. It's a calculator that factors in, so it uses a recursive relationship with a basis case of whenever you drop below 1, the remaining life is just set to 0, and it solves for the mean number of hits, and then from that computes the equivalent damage. It's okay. Some things that are unfortunately disappointing is you can't adjust, say, like in these equations, the percentage of resistance. You can't really factor in resistance like to physical damage and how that affects the probability. You can see from the options. You can change, of course, the type of monster, but then you can't really adjust for, say, the number of players in the game, right? So it'd be nice to be able to have more freedom to work with those variables. But furthermore, even this is an approximation for many of the reasons we've really discussed. It doesn't, factor in life regeneration, which you could actually include in the aforementioned equations if you wanted to. You could already take the base equations in this video, adjust them accordingly. For example, you could factor in probability to hit, etc., as well as include variables for the life regeneration, poison, damage, or etc. So you can do a lot more with these equations than just with this calculator, but it's still very useful and it's reasonably accurate. So I have the link is below, and if you'd like to use this calculator, it's a fair approximation. It has its constraints, but overall it's not bad. There are other problems, but they're much more technical and not really relevant for an accessible audience. So overall, I'd say this is a decent calculator. And just before I conclude the video, I'd like to thank viewers, and I'm really excited for Diablo 2 Resurrected, and I hope this channel moving forward will be kind of a source of exploration. It'll be a channel in which I kind of really dive into the mechanics and answer many of the burning questions, like should I use Grief Beast when doing a Whirlwind Barbarian, and is that a fact? Is there a relationship between Grief Beast performance and how I whirl? The answer is yes. And can it compete with Grief? Dual Grief, say. Dual Grief Berserker asks, is that or superior? The answer also is yes, it can, if they're not ethereal. Should I use a Death Colossus blade? Or how does the probability to cast Amplify Damage, how does that really mathematically, not just multiplying damage by 2, but how does that really factor in that probability to do it into my damage across time after multiple attacks? Can I actually account for that? And yes, you can. So really the aim is to concretize many questions like that. So if you have questions about skills, how should I be using Blizzard, right? What's an efficient way to whirl? What are some of the counterintuitive trade-offs between Whirlwind and Frenzy that are not obvious, that really come out from mathematical analysis, etc.? Questions like that, feel free to comment below, and please like and subscribe for future content. And thank you for your time and attention.